Section 6.4 is on logarithmic functions. This is going to be the first video. We're going to do two objectives. We're going to change between exponential and logarithmic forms and define what they are. And we're going to evaluate logarithmic expressions. Real quick, recall that all one-to-one functions, remember when we talked about one-to-one, that meant for every x, there's only one y. So all one-to-one functions have an inverse. And when we find that inverse, we just switched our x's and our y's, and then we would solve it for y. We have a new function, well, not really new, but our exponential function is defined by y equals a raised to the x. The inverse of this function would be, so x equals a to the y. So we're not even solving it for y at this point. Because this is so important of a function, it was given its own name, the logarithmic function. Or we'll see it as y equals log a of x. Now, some important things. We have our logarithmic function. So the base is a, and a's got to be greater than 0, and a cannot be 1. We define this function, or we denote it by saying y equals log a to the x. It's read as y is the logarithm with base a of x. So this is kind of how we would say it in words. So it's defined by that y equals log a to the x if and only if, this is important, x equals a to the y. So here we're changing it from log form to exponential form. The domain of this, which we'll talk about domain in a little bit, but the domain of this function is going to be basically all x greater than 0. In words, when you're doing this, think to yourself, a raised to what power give me x? That'll kind of help us when we go to solve these problems. All right, so example 1, we're relating logarithmic functions to, or logarithms to exponents. So I always write this down, the y equals log a of x, if and only if a, or x equals a to the y. I always write that at the top of my papers. You don't have to write the if and only if. You really just need this part and this part. I always write that just because it helps me to like see it every single time I'm working on these problems. So our first one in this case, we know that if y equals log base 3 of x, then if we rewrite in this in exponential form, x equals 3 raised to the y. So you gotta have to like rearrange, this base 3 right here, that little base 3, that becomes, kind of our base for our exponent. The y up here at the end becomes the exponent, and then that x here just moves over to the x there. So it's kind of weird just getting into that pattern of rearranging this. All right, now let's add some numbers into this. Let's say that we have y equals 4 and x equals 81. Then if we're looking at the log piece of it, we'd say, all right, well, 4 equals log 3 of 81. So log base 3 of 81, writing that in exponential form, 81 equals 3 raised to the 4th power. Which that's true, right? 3 times 3 times 3 times 3 gives you 81. So adding numbers in there, you're trying to see, well, this 3 raised to the power of 4 gives us that 81. All right, for example 2, change back color, sorry, example B, we have that y equals log 5 of x. So writing that in exponential form, you have that our x equals 5 raised to the y. Let's give it some numbers this time. So let's say y equals -1. Our x is actually going to equal 1/5, and I'll show you why. So in log form, you have -1 equals log 5 of 1/5. But write that in exponential form, we see that, all right, where was that? Oh, here we go. 1/5 equals 5 to the -1, which is true, right? We know how when we're rearranging our exponents, 5 to the -1, or when we write things like, x to the -1, it's 1 over x. Or 5 to the -1 gives us 1 over 5. For example 2, we're going to change from exponential form to logarithmic form. So we've got 3 examples here. Part A, we have 1.2 cubed equals m. So when we're changing this to log form, start with that, I kind of have it written on the side. Remember I said last time I always kind of write this down. So we start with that y piece of it, y equals. So in our case, y is the exponent. So y is 3. So 3 equals log. Now the base is a, so in our case the base is at 1.2. So 1.2 to the m, because just the x is left over, so that helps. The next one, e to the b equals 9. So let's see, the exponent part, b, that is our y. So b equals log e, that first thing, the a kind of when you take it back to the original equation there. That is our exponent. The last little piece there, that 9, is our x. Last one, a to the 4th equals 24. Well, y, the exponent is 4. So 4 equals log base a of 24. For example 3, we are now doing the opposite of what we just did. We're changing logarithmic functions to exponential functions. So our first one, log base a of 4 equals 5. So the exponent piece is, the y, the equals part. That base a there is our base, so start with that. A to the 5th equals x, or in our case equals 4. So start with the next one. E is your base, so e to the exponent, which is your answer over there, your y, -3. E to the -3 equals the last piece left over, b. Now do your last one. Base is 3, so 3 raised to the c equals 5. All right, example 4 is where it gets fun. So here we're going to find the exact value of a logarithm expression. So our first one, we have that log base 2 of 16. We're trying to figure out what this is. And what we do is kind of think, 2 raised to what power gives us 16. So I'm going to start by, I always like to put that y in front of that. So y equals log base 2 of 16. Now we're going to rewrite this in exponential form. Remember, these were our kind of exponential and log equations. I kind of always have them written there. So we want to rewrite this as an exponential equation instead. So 2 is our base. So 2 raised to the exponent, so raised to that y, equals x, or equals 16. So now we want to get them to have the same base of 2. Remember we did in 6.3 when we were solving exponential equations. That's what we just did. We have an equation like this. We have to get the bases the same. Fortunately, we know that 16 is 2 to the 4th. So we can rewrite this as 2y equals 2 to the 4th. At this point, you're just kind of dropping those 2's because y will equal 4. So the value of our expression, log 2 of 16 equals 4. All right, our next example from example 4, we have log base 3 of 1 over 27. So again, we're thinking 3 raised to what power gives us 1 over 27. So I'm going to add the y equals to this first. Now we're going to change it to exponential form. We change it to exponential form. So that 3 is our base, so 3, that y is our exponent, 3 to the y, equals the leftover piece, that 1 over 27. Ooh, 1 over 27, we can rewrite this as 1 over 3 cubed, but that still doesn't equal 3, which is what we had over here. However, remember our negative exponent rule, so that 1 over 3 cubed is the same thing as 3 to the negative 3. So, bring it back over here, we have 3 to the y equals 3 to the negative 3. We don't need those 3's. Y equals negative 3. So log base 3 over to 1 over 27 equals negative 3.